Let me start welcoming everyone to this first aviation application section webinar. So the goal for these webinars is to bring us together, even if virtually, but to bring us together more often than the annual meeting that we have. Also to have people talking, so giving a talk for us that could be a sort of inspiration, especially for young staff, but also for everyone, with new ideas and challenges. And with that in mind, to find the first speaker was not hard. We wanted to have a first seminar on topic related to the environment and energy transition. And because we like to see more works also at the aviation application section regarding to this topic. And so for me, it was really easy to identify Professor Henri Werij as our first guest speaker. Henri is the decan of the Faculty of Aerospace Engineering at the Delft University of Technology. He studied experimental physics at Leiden University here in the Netherlands, where he got his doctorate in 1988. And then he worked first at the Joint Institute of Laboratory Astrophysics in Boulder in Colorado, so in the US. Then for some time at the University of Amsterdam Research Center TU in the Netherlands, where he was the director of space and scientific instrumentation, before he became the dean at my faculty. Henri is an advocate of the urgent need for transition in the world of aviation. Sustainable aviation has become the main research topic in our faculty since he started his position as decan. And the goal for us is to support aviation to become climate neutral with a conscious and innovative research agenda. So I'm very happy that Henri accepted to spend some of his time with a very busy agenda to share with us some of his ideas and knowledge. Henri, thank you very much.
Thank you very much, Bruno. And I have to say, I enjoy very much talking about this topic, as you know. And I hope I can share some of my thoughts and hopefully inspire some people in certain directions as well. What I'm going to talk about is indeed the quest for climate neutral aviation, which is actually a bit more than just carbon neutral. Because a lot of people think that when we solve the carbon dioxide problem, then we got things settled. But unfortunately, this is not the case. But I'll try to give you an idea of the directions that the aviation industry is looking at, things that we are looking at in Delft together with many other partners and friends all over the world. And yeah, I also hope I can give you some new insights. First of all, a brief history on the evolution that we already saw in aviation, and that is regarding the energy efficiency. What I plotted here is a graph showing the amount of liters of jet fuel per passenger per 100 kilometer. And actually, these are numbers that you might see in your car. Of course, in Europe, it's liters per 100 kilometer. It's a bit different, of course, in other parts of the world. But what you can see here is that we have seen an improvement of about a factor of 5 during the last 60 years. And this is due to the advancement in aircraft design, weight of the aircraft, the aerodynamics, better wings, but certainly also improved propulsion systems. The original jet engines are completely different from the turbofans that we see nowadays, where we actually have a turbine which is driving the big fan in the front, and only a small part of the air is going through the turbine. The majority is actually going through the fan. Actually, right now, the energy consumption per passenger per 100 kilometer is comparable to what you see in a really good car nowadays. Of course, for a car, it also depends on the number of people you have in it. But typically, if you sit in a car just by yourself, your your fuel consumption is even higher than in an aircraft. So much said for that. But what we see at the same time is that we, over the last 7 decades, we have seen an exponential growth of air travel. We travel, more people travel, we travel more often, and we travel further. And this growth is continuing. Of course, we now had a dip due to COVID, but we see that things are picking up again. And we see a doubling roughly every 15 years. And the improvements that we had seen in aircraft design and propulsion engine design don't keep up with the enormous growth. And so this graph is going to the year 2012. Also in the years 2013 to 2019, the fuel efficiency worldwide improved by about 12%, but the revenue passenger kilometers increased by 50%. And that means that the contribution in CO2 emission of aviation is actually increasing. So if you look at the current situation, you could say fuel consumption per passenger per kilometer is comparable to that of a modern car, but it's the large distances and the massive number of passengers that we are transporting. So currently aviation accounts for about 2.5% of the global CO2 emission. And if in other sectors we would be successful, and we are hopefully going to be successful in bringing the carbon emission down, then the percentage of aviation will rapidly increase if we do not act. So we have to do something. And on top of that, it's not just the CO2, it's also the emission of NOx leading to ozone, it's the emission of water, contrails, thin cirrus clouds that play really a very important contribution to the global warming. And I will come back to that because this is a topic that we definitely have to take into account right now when we start developing new aircraft and new propulsion systems. So if we would like to do something about the climate effect of aviation, what knobs can we turn? And actually, there are quite a few, and they are all interconnected. So first of all, let's take a brief look at the forces acting on an aircraft. This is an aircraft in horizontal flight, where the gravity is actually counterbalanced by the lift of the wings, and the thrust from the engines is counteracting the drag. Well, here we have to do something, and obviously we have emission, and this emission is something that we would like to get rid of. So how can we reduce the emission? Well, first of all, we can replace fossil fuels by something else. I'll come back to that later on. Whatever you choose, always make sure that you have an aircraft which is as fuel, or should I say energy efficient as possible, which means a lot of lift, as little drag as possible, so high lift over drag, and a low mass, so it should be light. Make sure that you have energy efficient and clean propulsion systems, but also think about at what altitude do we fly, in what area, region do we fly, and how can we counteract the non-CO2 effects. And finally, also, if possible, use another transportation means than an aircraft. We don't always have to take a plane. So let's start with the first point, replacing fossil fuels. Well, that sounds, well, it's easier said than done. And what are the four main options that we have nowadays? First of all, full battery electric. You see a lot of talking about this. I would say that nearly every week it looks like a new company starts that claims that they are going to fly huge distances, at least several hundreds of miles, using full battery electric planes. So that could be an option. But electric could also rely on hydrogen and hydrogen fuel cells. Finally, hydrogen can also be burned directly, like we are burning in a combustion engine the jet fuel, the kerosene right now. You can use hydrogen, or we can replace fossil fuel, fossil kerosene, by synthetic aviation fuel. Could be made in the way of biofuel, or even better, and we would have to do that if you need a large amount of fuel, where the bio route is not going to work, simply because we need too much. That is when you use electricity to ultimately create fuel again, just like the fuel we are using nowadays. So biofuel, like I said, is not an option to replace everything, because we simply need too much land and too much water. So the replacement is using electricity, and if we do that, it should be green. At least it's now fossil sources should be included. And then it's all about how do we convert this green electricity into passenger kilometers. That is ultimately what counts. We start with green electricity, water, wind, solar. You also might, it could be that we, and quite likely that we also need nuclear power to get enough electricity in the end. And we do not want to waste this. This should be transferred in passenger kilometers. So how do then the four options compare? Well, the first thing you do is look, if we start from electricity, we somehow have to carry this on board of a plane and then bring it to the engine, to the propulsion system, which is going to be the most efficient. And there it's clear there is one winner, which is the full battery electric. So if you have electricity, you can very effectively store it in a battery. From the battery, you get it out very efficiently as well, and send it to a highly effective electric engine. So it's all wonderful. If you go the hydrogen fuel cell route, yeah, first we have to create hydrogen by electrolysis. Then we want to store them on board in a liquid form, so we need energy for liquefaction. Then we send it back through a fuel cell, we have losses, and then it goes to an effective electric engine. But overall efficiency is really roughly a factor of 3 lower than full battery electric. Hydrogen combustion is nearly the same. What we do there is we have hydrogen and we simply burn it. So we miss the fuel cell part, but the combustion engine is a little bit less efficient than electric engine, but it's roughly the same. And then finally, we can make synthetic aviation fuel or e-fuel by using electricity, create hydrogen, capture CO2 from the air, and work this into fuel again. There the efficiency is even lower. So you might think batteries is the way to go. And this is what we see in automotive. So right now for passenger transport on the road, yeah, energy-wise, the battery route is the way you should go. It's better than hydrogen, I would say. But is this true for aviation as well? And if you simply look at what all is written and all the new companies that start, yeah, I think it must be the case. I think this sheet I sort of explained already. So batteries are most efficient in terms of energy loss, from electric power to battery storage to propulsive power, highly efficient. Electric engines are also superior in terms of efficiency compared to conventional engines. So let's say you gain a factor of 2 compared to turbofans and a factor of 3 to piston engines. And in view of scarcity of sustainable electricity, we cannot afford wasting energy. So, well, should we go then for this battery route? It's a bit too easy if we only look at this aspect. And to take you along what matters, I take you into, it's not a lot of mathematics, but it's a range equation that you can easily derive essentially from the four vectors that I showed before. And it relies on the fact that the energy you need to travel a certain distance the energy is the same as the force times the distance. In other words, the distance is the energy divided by the force. And that's what I am putting in here. What you arrived then at is the range. If you want to go from A to B, you need a certain amount of energy in the batteries divided by the total mass of the aircraft, including passengers plus batteries, times the ratio of lift over drag. I'll come back to what this number actually means for pilots, times the efficiency of the propulsion system. So it's a very easy formula, which is perfectly true for battery planes where the weight is constant. If you would have a plane with fuel where you burn fuel, essentially the range per amount of fuel is increasing all the time because the plane becomes lighter during the flight. This is not true for a battery plane because the mass is always the same. So it's the total energy in the batteries divided by the total mass times the gravity constant times L over D times the efficiency. You can rewrite that by saying the energy divided by the total mass is the energy per kilogram of the battery. So it's the energy density of the battery times the mass fraction of the batteries. Let's say 10, 20, 30, 40% of the weight of the aircraft goes in batteries times L over D times the efficiency divided by the gravity constant. So let's see where we would arrive at with numbers that are at our hand nowadays. First of all, let's look at the ratio of lift over drag, L over D. And for those of you who are a sailplane pilot, they probably very much know what this number also stands for. The ratio of lift over drag is the same as the horizontal distance you can cover at the expense of the vertical distance lost. So for instance, if you have a sailplane which has an L over D of 27, it means in still air, so no headwind, no thermals, still air, you have a range of 27 kilometers for every 1 kilometer altitude lost. It's pretty good. A Sparrow, roughly 4. It's like a small flying brick, you could say. A small Cessna 150 is also poor. It's 8. But passenger planes like an older one, Boeing 767, and the newer ones, they are in the range of about 20, slightly more. Albatross, beautiful soaring bird, 20. And then sailplanes, they go up to 27 for the, let's say, entrance plane gliders. And for open class competition gliders, 50 or higher. But you have to keep in mind what this means to arrive at these high numbers. So one pilot, you're lying in there in a very streamlined position, leading edges, everything has to be kept extremely clean. Very large span for just one or perhaps 2 people on board, and it's not typically what we have in a passenger plane where we have engines sticking out as well. Well, so that's one thing, the L over D. Let's say we have something around 20 there. Now about the energy density. What we see now is for instance, for Tesla cars, the lithium-ion batteries they're in the range of about 270 watt-hour per kilogram. That is just for the battery cell. It's not for the whole structure, but for the battery cell, 270 watt-hours per kilogram. And the latest model Tesla, which has also the latest batteries, it did not increase the energy density. It's actually, it even for the first cars that came out of the factory, it was even a bit lower than the previous version. It's cheaper to make, but the 270 watt-hour per kilogram is still, yeah, it's very high. It's sort of state of the art what you can now get. In the future, we want to increase that, and let's say we could get it to 400 watt-hour per kilogram. Sometimes you hear parties say they think they can achieve more, but when I talk to battery researchers, professors at our university, but also international ones who are in the battery field, they say, well, this is already really challenging if you want to combine this with a long lifetime. A battery is pretty useless if you can recharge it 10 or 100 times and then it decays rapidly. It should last for thousands of recharging cycles, and that is a very strict requirement as well. Well, the 270 watt-hour per kilogram, or even the 400 watt-hour per kilogram, if I compare that to kerosene, and what I show in this graph is for the same amount of energy stored in 1 kilogram of kerosene, how many kilograms of lithium-ion batteries would I need? Right now, that would be 44 times more. 44 kilograms of batteries having the same amount of energy as 1 kilogram of kerosene. At the same time, the volume would be 18 times as much as the volume I would need for kerosene. In the future, again, going, let's say, to 400 watt-hour per kilogram, weight-wise, it's still a factor of 30 worse, and volume-wise, it would be a factor of 12 worse for batteries. But we are not completely there yet. What I'm talking about is lithium-ion battery cells. And these battery cells, they have to be packed in a whole system for thermal management in a strong structure, and that will lead to additional losses. So what I put down here, we have to take into account that there are temperature effects, and certainly in a plane flying at a higher altitude, not only flying during nice summer times, you have to take into account that you have losses due to low temperature and energy needed for heating. For those of you who are driving an electric car, you know how much your range is going to decrease in wintertime. And I can tell you in my car, it's more than 20%, but let's say it's about 20%. We also have to take into account that batteries degrade, and the degradation you have to take into account right away. You cannot sell a plane which is meeting its specs on day one and not anymore after that. So you have to take into account 10% there. Packaging right now for the Tesla Y model, they are doing it really in a very effective way. They add only an amount of mass that the energy density goes down by 34%. NASA thinks that for aviation, well, you should lose 30%. I'm even a bit more optimistic. I said, let's say we achieve only a loss of 25%. Well, when you're flying, you have to take into account headwind. Typically, let's say you have a propeller plane flying 400 kilometers per hour, 40 kilometers per hour headwind is not that much. So the 10% is rather optimistic. And you never fly in a straight line. You have standard instrument departures, arrival routes, and that means that we, on average, lose another 10%. That's a number that you for sure will recognize. Altogether, we already lose 56% of the original energy density. But this is not the whole story yet, because the point is also that we need a reserve. And this reserve is very substantial. We have to take into account that we need a reserve for flying a holding pattern. You have to be able to do a go around. So you start the landing and at the last moment you decide to not land, climb again. You have to be able to divert to an alternate airport. And when you arrive there, it is required that you still have energy for 30 minutes of flight, just for safety. Unlike a car, you can decide to arrive at the charging station being empty. In aviation, this is not what is allowed. And if you take all of this into account, then this roughly leads to a reserve range that you need on the order of about 250 kilometers. So if we stick the numbers now in that we previously already had, let's say we have 300 watt-hours per kilogram. So this is better than what we have in the cars right now. We have an L/D of 22, which is also really good. This is an optimistic number. We take an efficiency of 80%. It's also on the optimistic side. And then we say we have an aircraft where 50% of the mass would be available for batteries plus payload. This is a high percentage. Typically, it's a bit lower. But let's say we are capable of designing planes in a different way. We have 50% of the takeoff of the takeoff mass or the maximum landing weight, whatever. It's the same here for batteries and payload. And we have the reserve of 250 kilometers. We can calculate the range, the effective range that we will have, depending on which percentage of the aircraft is going into the batteries. And if, for instance, here on this graph, I say I use 40% of the weight for the batteries, for the battery packs, leaving only 10% of the weight for the passengers, where it's normally would be up to 30% in a normal plane, then I arrive at a range of less than 100 kilometers, which is obviously a lot less than what a lot of parties now try to tell you. And this is really pretty basic high school physics. At the same time, if you only have 10% of the weight reserved to passengers compared to 30%, the energy needed per passenger goes up by a factor of 30 divided by 10 by a factor of 3. I can increase the range a bit by using more weight for the batteries. I could go to 45%, and then the range, great, will go to 130 kilometers, still not a lot, but then the energy per passenger is now suddenly a factor of 6 worse. So we are using energy to transport the batteries, and this is not what we want to do. Sometimes you hear Elon Musk say on YouTube that, wow, if we have batteries of 400 watt-hour per kilogram, then we are good enough for aviation. And he even starts dreaming about supersonic flight. This is really absolute rubbish, if I may say so, because even with the 400 watt-hours per kilogram, if you put it in, you arrive at a range of about 200 kilometers, unless we would do really incredible things to the L/D. And that this, I can tell you, this is really hard. So, perhaps also another myth buster. People, you hear people say, yeah, but yeah, we can use a range extender, put solar cells on the wings of your plane. And yes, it has been done. We have here an experimental aircraft, of course, no passengers, 600 kilogram, a huge wingspan of the order of, what was it, a 747, this order of magnitude, very light. It was so light that it essentially, when it hit some unexpected turbulence, it broke in the end. But there you could stay aloft, but you would need huge wings to capture the light, of course, only working during daytime when the sun is coming straight from above. It can be used for very low, slow flight and a very slow, very small payload. In Switzerland, they are trying to reach the stratosphere with a plane which will be solely relying on solar energy on the wings. But if you calculate this for a normal plane, yeah, what you can get is about 1% of the energy needed in cruise under ideal conditions when flying over the equator at noon, when the sun is coming straight from above. And yeah, let's say we have energy for the onboard entertainment system, and this is it. So this is not going to be a solution. So battery planes up to a short distance. And what would this now mean for the total challenge that we have in making the world of aviation more sustainable? For that, is important to take a close look at this graph. And it might look a bit complicated at first, and I try to explain you it's not. This is showing you the cumulative number of flights up to a certain distance and the cumulative amount of fuel up to a certain distance, where ultimately everything goes to 100%. And what we see here, for instance, if we would consider flights up to a maximum distance of 1,500 kilometers, we see that this amounts to 75% of all flights worldwide. So 3/4 of all flights worldwide are less than 1,500 kilometers, but it only amounts to 1/3 of the fuel used. If we are looking up to a distance of 4,000 kilometers, we see that it's 95% of the flights, and it's about 2/3, 65% of all fuel used. So it's good to keep in mind that 1/3 of the fuel worldwide is being used for flights up to 1,500 kilometers. 1/3 is being used up to 4,000 kilometers. And for the 5% of the flights for a larger distance, they are using the rest of the 1/3. Now, of course, the distance is more, but we are also carrying fuel to carry fuel. But it's mainly because of the huge distances that it counts harder. So what would this then mean if we look at the battery planes I just talked about? So I already said that the range is limited to very short ranges, 200 kilometers perhaps. The reserve, holding go around diversion to alternate airport plus 30 minutes left really spoils the case. And if we look here and say, well, up to 500 kilometers, it's 30% of the flights worldwide, but only 6% of the fuel. If we go only to 200 kilometers, what I just calculated, yeah, what we are talking there, that's a few percent of the flights, but it only accounts for roughly 1% of the fuel used worldwide. So if we talk about battery planes, just pure only batteries, this is not going to save us, because we are talking about a 1% level. I'm not saying that we shouldn't do it, and there are certainly cases where you can and should do that, but typically this is not going to be the big world saver, for climate effects from aviation. The point, however, is since this reserve is so detrimental, if we can take another energy carrier on board for this reserve, then things become more interesting, and this is creating new possibilities. And one of the serious options there, and it's an obvious one, is the use of hydrogen, and hydrogen with fuel cells. Again, I'm here in the same graph I showed before, where I compare now liquid hydrogen to kerosene, and then I see that the energy density for hydrogen is roughly 3 times higher than per kilogram than it is for kerosene, for jet fuel. However, you need roughly 4 times more volume, and not even taking into account the tanks it has to be stored in, and it will have to be stored at cryogenic conditions. Under pressure of 1 atmosphere, the liquid hydrogen has a temperature of 20 Kelvin, minus 253 degrees centigrade, and we have to keep it that cold. So, but you see, mass-wise, actually, hydrogen is very interesting, where, of course, we have to take into account the weight of the fuel cells and everything like that. So, for hydrogen fuel cell electric, a lot of research is going on there right now, and you see that several companies all around the world, and also in Delft, even a student team from our university is building a plane that is going to rely on hydrogen fuel cell, and they want to take liquid hydrogen on board. So a lot is going on, but also there are some issues. One of the issues is power density. And power density is the amount of kilowatt per kilogram. So for batteries, it's mainly the energy density. So it's the joule, the megajoule, or the kilowatt hour per kilogram. Here it's the kilowatt per kilogram that is a limiting factor. And it could mean that we need batteries during the takeoff and go around phase. So again, also for hydrogen, it's important to have some batteries on board. So it's, before I said we need hydrogen as a range extender for the batteries, but we need the batteries as a power extension for hydrogen. So this is interesting to keep that in mind. What we also have to take into account. Yeah, sorry.
We have 10 minutes just to.
Okay, I'll be fast, Bruno. It's if we look at other issues, the thermal management of the fuel cells is important. So if you have fuel cells with an efficiency of 60%, that means for every 6 megawatt we create 4 megawatt of heat. And the bigger the systems, the more important it gets, because the surface to volume ratio changes. And of course, we have to store. So these are things that we are actually have to work on very hard to make hydrogen fuel cell electric the way to go. But like I said, there are many places in the world where this now is going on. Universal Hydrogen in the US, Zero Avia in Europe, Zero E Airbus is looking into that, Aero Delft in Delft. So a lot of work is going on there. Then finally, looking into hydrogen again, hydrogen combustion is also a serious possibility. And that might be perhaps for a range more than 1,500 kilometers. I don't know where the cutoff point is going to be, or for larger aircraft, then hydrogen combustion is an option that is also currently investigated by many parties. Rolls-Royce, Airbus, TU Delft, many other places are working into that. This finally is a graph where I show the importance of hydrogen anyway. So if we start with electricity, we can, by electrolysis, create hydrogen. But when we combine that with CO2 captured from the air, direct air capture, then we can work this into sustainable aviation fuels, e-fuels. And so hydrogen, nevertheless, for regardless of what you do, is the option to go for aviation. Perhaps I can skip this one. The point is we need a lot of energy to create the energy on board. For instance, if you would like to make all the jet fuel in the Netherlands from electricity, we would need 22 gigawatts of green electricity on a 24/7 basis. And I can tell you this is all wind power that we hope to get in 10 years from now at sea. Also, to give you an impression of what we are talking about, this is currently the biggest wind turbine at sea in the North Sea. It's the V164, and the 164 is the diameter of this wind turbine, more than 80-meter blades. compare this to the biggest aircraft that we know, it's the A380, or the biggest passenger aircraft, and we put them to scale, you see it's a small plane versus a huge wind turbine, and then look at the energy that we need. And the wind turbine peak power, roughly 9.5 megawatt peak, 5.5 megawatt average, and the aircraft on the order of 100 megawatts. So you get a little bit a feeling of what we are talking about. So it's all about energy need, and that also means that we have to be very careful about how we are going to use this energy. So we will not have enough for a long time to go because we need so much. There also will be competing markets. So the world is not waiting for aviation to use their green electricity and their green hydrogen. So this is something, and this means that whatever we do, green energy should not be wasted. And that means, yeah, in other words, the greenest energy is the one that we do not need. So make the aircraft as energy efficient as possible. Well, that's one of the things that we're working on in Delft, together with Airbus, together with KLM. It's a new concept, which is interesting because the shape also allows to carry hydrogen on board. I'm not saying that this is ultimately going to be the plane that we are all going to fly in, but it's really a serious concept that is being studied. I also would like to make one remark on supersonic flight, and I think this is important too. I read, and especially in the US, people dream about supersonic flight again, and then it said, well, this is sustainable because we use synthetic aviation fuels, so therefore it's green. Well, to be honest, I don't think so, because the fuel that you need per passenger per kilometer is roughly 1 order of magnitude 10 times higher than what you have in a subsonic economy seat. So this means that you're really wasting the energy that we don't have enough. And then furthermore, due to the very high flight levels that you use, the non-CO2 effects are very much more severe than what we have in current aircraft. So this is definitely, in my opinion, not the way that we should go. So this brings me back to the point of climate impact is not just CO2. It's also what kind of clouds do we create. Here we see some contrails. This is a picture I took from my study room at home. And what you see contrails. There was a certain wind gradient, and you see these contrails actually spreading in the horizontal direction and creating a fairly stable cirrus cloud, and that acts, this was in the evening, as a blanket also for the Earth, for heat escaping. And this is what we have to take a look at as well. And this is being done too, because where you get these contrails depends on what altitude you fly, what the humidity is, what wind gradients are, and you can look at the atmospheric conditions. And sometimes we're flying a little bit higher or a little bit lower. You can actually minimize these effects. And studies are currently going on. Also here in Delft, colleagues Esther Rosenbrand, H.G.C. Sun, Jaco Hoekstra, they did a study where they said in areas where people fly a lot, what kind of gain could we get by simply flying a few, let's say, a few thousand feet lower or higher? How much could we gain? And the gains we could get there, they are really tremendous. And obviously, this is going to have an impact on operations as well. And I think for all of you, this is important too. So if you look at the changes that are occurring in aviation right now, it's obvious that there will be big challenges to airport facilities. So if we have batteries or hydrogen, we need significant changes to the infrastructure. We need charging facilities, hydrogen storage. Perhaps we even want to liquefy on site. That is something to be looked at. But also in the air traffic management, when we want to optimize flights for climate effect mitigation, then we will have to take this into account for the air traffic management. Rerouting and flight level reassignments are going to be important. Well, anyway, I hope I didn't talk too long, but it brings me to the conclusions. There is no one silver bullet for replacing fossil fuels. It depends on the range that you fly, the number of passengers, and we have several options. And what is the best option for a certain range has to be seen, but yeah, I sort of sketched what we are currently looking at. Also very important to remember is climate neutral aviation requires more than carbon neutrality. That is really a very important point. Obviously, all that we do will have a big impact on airport infrastructure and air traffic management. And finally, I would say perhaps the most important message, regardless of the choices that we make, conscious use of the energy is crucial. Whatever we do, we have not to be wasteful. And this is what I wanted to tell you.
Thank you very much, Henri. No one can talk, but thank you very much. It's time for questions. We have 10 minutes, so eventually we have time for 3 or 4 questions. There's one already in the chat, so we'll start with that one, but then I'll invite people also to unmute themselves and ask the other questions. So Henri, Marius refers, well, first he thanks you for your presentation. Then it mentions about this argument that emissions in a high altitude have much higher impact on the ozone layer than the ones that are produced at the ground level. This statement stays in the case of atmosphere that is not stable with winds and weather impact on these emissions.
Yeah, it's not just about the ozone layer, and I have to admit I'm not the expert on these effects. So there are other colleagues in Delft who have been working on this. Also at MIT Aero, they have been studying this as well. But if you go high in the stratosphere, the processes taking place there are different, and also the lifetime of what you deposit there is longer. And if what the researcher that studied this, what they say, the effects of depositing your emission there is larger than what we than the climate effects of emitting lower, where there is more turbulence and where you finally, where the lifetime of your emission is less. But again, I think Bruno in Delft, it's people like Feija Jin and Irene Deducy who can tell you a lot more about that.
Yeah, so Marcus, if you want to know more, just contact me. More questions. I presume that people can unmute themselves and ask questions. I have a question if there's no other questions for now. Oh, there's a question here. So what? Yes.
Hi. Good morning, I guess. Thank you for the presentation. Very interesting. Just a quick question. If there's new aircraft, I'm thinking here about the sort of secondary implications for complexity for air traffic management. When it comes to these new propulsion systems, do you foresee that will lead to new airframe designs, which in turn might lead to different operating characteristics, like the typical speeds and level performance?
Yeah, I think it's quite likely. Yeah? If you indeed keep in mind that we have to take care of our energy use a lot, then perhaps changing your flight levels might be an issue to look at. And also your speed might be something to be compromised. Perhaps flying a little bit slower could be better energy-wise, but of course this will have an impact on the business because your turnaround time increases. And if it means that you can fly your plane only back and forth 2 times a day instead of 3 times, that will have an impact. But all of these things have to be looked at. And certainly, if we want to take hydrogen on board, which needs a lot of volume, I can tell you this will require different planes as well. We need surface for cooling. This is what we see now already for the electrical engines which use hydrogen. You see apart from the very small planes, you already see that there is cooling surface required. You will see that a storage volume is required, and that's what we have in the Flying V as well. But there certainly will be an impact for sure. We have to we have to keep in mind that it has to fit the system as we have it today. The Flying V, for instance, has been designed such that it fits the current gates. We don't want to have a full new infrastructure at airports.
Okay. I was thinking that's an interesting point. I was thinking on the lines of if you end up with more novel types of aircraft before they become mainstream, you have potential for more diversity of aircraft performance, and therefore you've got a more complicated set of traffic flows to balance. Create some more optimization challenges.
Absolutely.
Okay.
And certainly when we talk about flight level change, it's easier said than done. Oh, please fly 2,000 feet higher because of the cloud formation. There has to be space available. But I think these are the things that we will have to look into.
Okay, excellent. Thank you.
We have,
You're welcome.
Thank you, Jamie. Lavanya, please go ahead.
Hi, everyone. Great talk. Thanks for organizing this, to the organizers and to Henri for the very interesting presentation. I was thinking about the something related to the previous question. If you have this heterogeneous types of fleets of aircraft, say electric for short range and hydrogen for longer ranges, etc., etc. But even as the fleet mix is evolving, and even let's say 10 years, 15 years down the line, what new operational implications are there from an airline and even a traffic management point of view? And that's a very broad question, but it just sounds like we have to rethink spacing requirements in the air. We may have to rethink the design of airline networks and so on and so forth. How do you think about this?
Yeah, it's an excellent question, and it's certainly going to play a role. Imagine that we are going to have aircraft where some of them use electricity, even though percentage-wise it's not a lot. It will require a lot of electricity. We will have hydrogen on the aircraft, and we have to load that and tank that, and it's going to be a challenge. Look at the challenges that we face in the space industry, where sometimes a launch is aborted because of fueling problems of the hydrogen, and now we have to do it on a continuous basis. So that's going to be challenging. Plus, we will have the biofuel and the sulfur and whatever. And to be honest, these topics are the things that we want to tackle in something in a program that we started. It's called Flying Vision, where we bring knowledge institutes like TU Delft together with aircraft manufacturers. In this case, it's Airbus we have on board, but also an airline. We have KLM, they are involved, and an airport, a big airport in the Netherlands, Schiphol. And these parties together are going to study indeed all these effects, because the choice of one option will have a huge impact on one of the or more of the parties, and everything is connected. And therefore, the airline company, they want to directly talk with the aircraft manufacturer and vice versa, and the airport as well. So it will be a topic of a lot of further study, but we have to start now. And actually, this is what is currently being done already.
Okay, great. Thank you.
We have, thank you, Lavanya. We have 2 more questions in the chat. Mario, sorry, we'll give priority to the other questions because you already have your question, but we can follow up per email if you want. Ankita Sharma asks, what will be the impact of policies like CORSIA on aviation? What do you think, Henri?
Yeah, I think ultimately we need a strong incentive from governments in order to make things happen. So regulations are and requirements that we also get from policymakers are going to be very, very important. And what also, yeah, we talk a lot about level playing fields. And I'm not sure if you get a level playing field for all of the world right away, but certainly for regions, it should be clear what to be expected there. And so things like CORSIA are very important. We set ourselves a goal, but and it's good that the industry and the sector itself is taking these steps. But I think at some point, also at a high level, it should be decided that this is what we really will have to do.
Good, and last question from Gonan Louis. In the short, what is asked is, can we replace fuels? We need this reserve fuel. Can we use then electricity or renewable or source of energy to operate these reserve fuel parts?
Yeah, that was the whole point. So if you, let's say if I could use the 250 kilometer from the batteries, having another reserve at hand, then the range of battery electric becomes larger, obviously. And this is the whole point. This is what we would like to achieve. We have to take something in case of.
Yeah.
And the question is, what do we do in case of? Is that going to be jet fuel? There is a lot of talk about a hybrid propulsion system and hybrid aircraft. But I think a very interesting way is to go the all-electric way, where you have the reserve essentially is hydrogen. And if you go the hydrogen route, we think that we can achieve much more than just the range we have now plus the reserve. I mean, yeah, even 500 kilometers would be really nice already. And then we talk about 6% of the fuel, and then it becomes really interesting already. But what if we could go to 1,000 kilometers or 1,500 kilometers? And this is what people are after right now. That's what Airbus with their Zero-E project is after. They are thinking about an ATR type plane, 70 passengers, something like this. Propeller, electric propeller up to, yeah, let's say 1,000, 1,500 kilometers. I'm not sure. And above that, you go to hydrogen combustion. That is what they are looking at. But it's...
Okay. Thank you very much, Henri. Thanks for your time. I think it was a great talk. And there's probably many more questions. Like Marcus has a question, they can email me.
But yeah, Bruno, indeed, if you can collect questions and we can answer them, then...
Yeah, I'll do that. I have an email in the next slide. I just want to share 2 slides before everyone goes. So the first talk will be given by Rodrigo Acuna Agost. So I think some of you know him. He's sometimes present at our annual meetings. He's also frequently present at Agiforce meetings. He's the head of AI research at Amadeus. This will be on June 13, same time slot. And we're talking about applications and challenge of AI and operational research in the travel industry. And I also want to call your attention to submit abstracts to the Inforum's annual conference. It's time for that. Maxley is the current is a cluster chair. If you have any doubts about how to submit or in which session you can be part of, and also it's open already the submissions for the 2023 Best Dissertation Prize. Vikrant Vaz is the head, the chair of the committee. Deadline is June 1st. There will be also soon news from regarding the Best Paper Award and also Best Student Presentation Award. So Sebastian and Gianmarco is present, are the ones sharing these committees. If you have any questions to them, just let them know. Also on the side, Agiforce, they also have applications open for the Anna Valicek Award competition. Please check on Agiforce website and become member of our section, where we'll have more of these webinars where you can contact and have access to this information. And if you have questions, there is my email and I'll collect them. I'll make sure that together with Henri, we'll get, or colleagues here at TU Delft, we get an answer to you. So with this, I close here the session once more, thanking Henri for his time, for his valuable talk, and thanking you for attending this webinar, with a specific thank you very much to Lishwa and Nunu to help me to organize this webinar. And I hope to see you soon, if not before, for the talk of Rodrigo in June. Have a nice day, evening, night, morning.
Yes.
We stay in touch.
Thank you,
Thank
Bruno.
you, Henri.
Yeah,
Thank you, Henri.
thanks everybody for your patience. It was a long, long session.
Was nice. Thank you very much, Henri. Thank
All
you.
right. Yeah, bye-bye.
Bye-bye. Good. Thank you very much, Lishwa and Nunu.
Thank you.
Thank you, Bruno.
Bye.
It was
Contact.
great. Yeah.
Bye-bye.
Bye.